Good morning, friends. Now, in chapter number 12, Electromagnetic Induction, in this chapter, we have studied our next topics energy density of a magnetic field. Consider a long solenoid having length is small l. Near the middle, cross sectional area is capital A, and carrying a current, it is I, through it in solenoid. The volume associated with the length is small l. It will be A into L. The uniformly distributed energy, that is UB, stored by the length is small l of the solenoids. It must be lie entirely within the volume is AL. The energy stored will be uniformly distributed within the volume as the magnetic field vector B is uniform everywhere inside the solenoid. It is as shown in figure. Thus, the energy stored per unit volume in the magnetic field is UB is equal to UB upon AL. But small ub is equal to 1/2 Li square. Into 1 upon AL. Then UB is equal to, in brackets of capital L upon small l, into I square upon twice. For a long solenoid, the inductance capital L per unit length is given by UB is equal to inductance per unit length multiplied by I square upon twice A. Then the given equation, small ub is equal to, in brackets of the inductance per unit length is equation mu 0 n square into capital A area into I square upon twice A. Then ub is equal to 1/2 mu 0 n square I square, where L is the inductance, small n is the number of turns per unit length, and A is the cross sectional area. For a solenoid, mu 0 is the permeability constant for air. Its particular value is 4 pi into 10 raised to minus Tm, Tesla meter per ampere, or 4 pi into 10 raised to minus 7 Henry per meters. For a solenoid, the magnetic field at the entire points in a solenoid is B is equal to mu 0 I n. Therefore, the expression for the energy density UB stored in a magnetic field can be written as, we can get UB is equal to B square upon twice mu. This gives the energy density stored at any point where magnetic field is B. Now our next topics are mutual inductance. It is denoted by the capital M. Consider the two coils placed side by side as shown in figure. Let's current I1 flows through the coil 1. Due to the current, a magnetic field B1 in brackets of x, y, z will be produces in the nearby the regions surrounding the coils first. Let's phi 21 be the magnetic flux linked with the surface area of S2, that is S2 of the coil 2 due to the magnetic field vector B1, and can be written as, we get the equation phi of 21 is equal to integrations of vector B1 into vector dA. If the position of the coils are placed in pace, then we can get phi 21 is directly proportional to I1. Then phi 21 it is equal to constant I1, or phi 21 is equal to capital M21 into I1, where capital M21 is the mutual inductance or coefficient of mutual induction of coil 2. The magnetic flux phi 21 will change in proportional as I1 changes, that is E21 is equal to minus d phi 21 upon dt. Then we can get the equation E21 is equal to minus M21, it's put the value of phi, into di1 upon dt. Now we allow current I2 to flow through a coil second. On account of this current, magnetic flux phi 12 link with the coil first is obviously proportional to the current I2. That is, phi 12 is directly proportional to the current I2, or phi 12 is equal to M12 into I2. Here M12 is the mutual inductance of coil first with respect to the coil second. Therefore, the induced EMF in the coil first will be E12 is equal to minus d phi 12 upon dt. Therefore, we can get the equation E12 is equal to minus M12 di2 upon dt. By symmetry, therefore, it may be noted that by symmetry M12 is equal to M21 is both are same is equal to capital M. The mutual inductance capital M of the two circuits or coil is the magnetic flux phi S linked with the secondary circuit per unit current IP of the primary circuits. Therefore, we can get here capital M is equal to phi S upon IP, or phi S is equal to MIP. For Faraday's law, ES is equal to minus d phi x upon dt at secondary coil is equal to minus d upon dt in brackets of MIP. Therefore, we can get the equation ES is equal to minus M dIP upon dt, or we can also state capital M is equal to mod of ES upon dIP upon dt. Hence, the mutual inductance is defined as the value of induced EMF produced in secondary circuit per unit rate of change in current in the primary circuit. The unit of mutual inductance is Henry. Therefore, Henry is nothing but to the Henry is equal to voltage upon AS, that is equal to ohms. Then 1 Henry is equal to 1 ohms. Therefore, the definitions are 1 Henry's definition we have get here. If the corresponding to 1 ampere per second rate change of current in the primary circuit, the induced EMF produced in the secondary circuit is 1 volt. Then the mutual inductance capital M of the two circuit is 1 Henry. Now the next are coefficient of coupling between the two circuits. The coefficient of coupling, that is K capital, is measure of a portion of flux that reaches a coiled second within vicinity of coil first. Therefore, we can get capital M is directly proportional to E21, where E21 it is the induced EMF developed into the second coil due to the portions of the flux from coil first reaching coil second, but the induced EMF is proportional to the number of turns of the coil. E21 is directly proportional to N2 K phi 2, but we know phi 1 is directly proportional to N1, then E21 is directly proportional to N2 K N1. Also here L is directly proportional to the N square, or capital N is directly proportional to under root of capital L. Therefore, we have write down N1, N2, it is directly proportional to under root of L1 in second under root of L2. Both are is equal to under root of L1, L2. Now, the equation is given E21 is directly proportional to K under root of L1, L2. Now replacing E21 with M, then we can write down the equation capital M is equal to K. It is outside the under root. In under root L1, L2, that is capital M is directly proportional to E21. Therefore, K is usually less than the unity. If K is equal to 1, the two coils will be perfectly coupled, and M is equal to, it is under root of L1, L2. If K is smaller than 0.5, the coils are loosely coupled. If K is greater than 0.5, then the two coils are tightly coupled. And third, if L1 is equal to L2, then the coil with self inductance, that is capital L, is coupled to itself with mutual inductance. Then we can write down the equations. M is equal to under root of L1, L2, that is L1 is equal to L2. Therefore, we can write down here under roots of L square. Then outside the under roots, it's only presence of L. Therefore, M is equal to L. This is the equation.